Hello, friends, and welcome to Train an AI to Play Chess Part 2. I am super thrilled to have you here. We are really going to get serious today. We are going to check back in on our leaderboard. We are going to review everything that we covered on Monday. It's been like 4 days now, so we'll kind of go over all of the basics that we learned back then. We will figure out how to save a model. This is not something we've done so far. Is all of the life of the model has been kind of in this microcosm of training the model and then making it have to do predictions, and then by the end of it, it's just gone, right? So we'll figure out how to save a model so we can save time in the future. We're going to learn about overfitting. A joke that I have is like, it would not be a global hack week if I did a session on machine learning and didn't talk about the dangers of overfitting. So we will get into that. And then finally, if we have time, we will look at something called ensemble models. The really quick teaser is you can build models that specialize in different things. And in chess, the sort of classic idea is that the beginning of your game, the opening of your game is a certain skill set, and then the mid game is a certain skill set, and then your sort of end game is a separate skill set. And so, like for example, I know that I actually have a pretty bad mid game. My end game is okay, but my mid game can be pretty sloppy. So we'll look at, can we train separate models to specialize in these separate phases of the game and perform better? So that is what we have to be excited about. Drop in the chat and say hello. One, what you're drinking right now. I'm drinking some tea, which honestly, it's probably a little bit late in the day for tea for me. It's 6, but I'm having some Earl Grey. Boom. Let me know what you're drinking. Also, let me know if you have any questions. I know it's been, as I said, 4 days since we started this journey of teaching an AI to play chess. So let me know if there's anything that you are confused about or anything that you want to dive into deeper. Other than that, we can just dive in and get going. So we will start by just checking in on the leaderboard. So if you were not here for the first session, I would totally recommend that you go and watch it because it was a great session. We had a lot of fun. But if you were not there, we participated or started participating in a Kaggle competition. And Kaggle is this super fun site, basically where you can build an AI and have it compete against other AIs at different tasks. So for Global Hack Week this week, we have a competition where everyone's trying to train the best AI to play chess, and they'll compete. And so I will share the link to that. In fact, I'll share the link directly to the leaderboard. And if you were not here for part 1 and this seems interesting and you want to get in on it, you still have time. In fact, we can check when the end date is. I'll start sharing my screen. Boom. This is my special host view. Okay, yeah, we currently have it set to end. What is this? I guess that is tomorrow at midnight. And I believe this is my time. So it'll be tomorrow. Oh no, it's in UTC. So tomorrow at midnight, I guess that is in more than 24 hours, should be. You have more than a day to get in there. We have lots of great submissions on our leaderboard. So first of all, everybody gets some props just for submitting. So if I will remind you, there are 4 swag drops that we're going to give out, and one of them is going to be to whoever is in first place. But not just of the public leaderboard, but of all of the competition put together. Then we'll do 2 more swag drops, randomly selected from anybody who's submitted anything. So just getting a submission in there sort of gives you a shot. Oh my goodness, Brittany. Is this Brittany of Global Hack Week's past? If this is you, say hey in chat. I believe Brittany won one of our Kaggle competitions like forever ago. And then, so those are 3 of the swag drops we're going to do. The first place winner, and then 2 randos from the leaderboard. But then we are also going to give a swag drop to somebody who submits a notebook. And nobody has done this yet. It's just me, and I can't win it. So right now, if nobody else submits one, you could just submit anything as a notebook, and you will win. But I will show you how to publish a notebook sort of a little bit further on. If there are multiple notebooks, I will pick one that I think is particularly nice. Or maybe more, but at least one. So that is sort of our check-in on the competition. If you are new and you didn't come to part one, I would say, one, go watch part one. It was great fun. But also, these 3 notebooks are sort of your guide to jumping into this competition. Part one, and this I guess we'll go into our sort of review here. So part one, we just looked at, I'm going to skip that bit. We just looked at this library called Python Chess that lets us sort of play around with a chessboard. One of the really powerful things it lets us do is see all of our legal moves, because if you didn't have this, you would first have to code up all of the rules of chess first and then train your AI. But here, we already know what the legal moves are, and we can just train our AI to pick one of them, which is super nice. And we looked at our sort of notation for moves and how to specify this is the move you should make. So the reminder is every move has 2 parts. There's the square you're moving from. Also, let me know if this is too zoomed in or too zoomed out or something. I can make it looks pretty small. Make it a little bit bigger. So here we're saying, oh, move something from square C2 to square C3. And that's what happens, right? So this is column C and row 2 is the from square. And then column C, row 3 is the 2 square. And we move our pawn forward 1. And so then we went on to look at this notation, this fen notation, that just lets us specify a whole board in a little string. OMG, it's Polar Void. Welcome, welcome. It's good to see you. And we were just reviewing sort of the basics of chess notation here. And so the important thing was that this little string, it can specify a whole chessboard. And you can kind of break it out and you can see, okay, there are rows. And then if you turn the numbers into spaces, you kind of get a board that looks kind of like this, which is super nice. With MacGyver hair, I don't know, is that what you call this hair? I need a haircut. It's been on my list of things to do for honestly weeks, but fun stories. My boyfriend got sick, and then I got sick, and then my boyfriend got appendicitis, and we were in the ER for like a day. So lots has come up recently, but I hope you're doing well, Polar Void. I hope things are killing it. And I think that basically sums up our review of this part one, where we just looked at how to interact with a chessboard in Python. Then part two, we looked at what are the basic building blocks of building a model to play chess. So remember, the overarching goal is to build a function that takes in a chessboard and then outputs a move, right? And so our first very simple way of doing this is just picking a random legal move, right? So you can accept this is what our board looks like. Oh, fun. Our board looks like, that big string of characters. And then we can get all of the legal moves from that board. And then we can just randomly pick one, right? That's what random choice does. And this was not a very smart model, but it technically plays chess. So we built this little game loop to play chess with us, where we, as the user, gets to put in a move, and then the AI responds. And we played against that AI, and it was just, it wasn't really intelligent, right? It was artificial, but it was not intelligent. So we had to start thinking about how can we make this function that takes in a chessboard and outputs a move, how can we make that better? And that is, of course, where machine learning comes in. And there are these 2 ideas where we could have a policy that actually does the work of taking in a chessboard and outputting a move, or we could have what's called a value function, where we just sort of evaluate how good is this board. And the cool thing about using a value function is that because we already know what moves are legal, our value function can just look at all of the possible boards that would happen if we played a move. And we can basically just decide, well, what's the best next state, right? Which move results in a board that is the best? And so that's kind of where we landed with our model, is we want to train a model that just takes in a chessboard and outputs, how good is this, right? Is this really, really good for us? And so we did some work to one-hot encode all of our pieces and then stack all of our pieces together. We'll be using these functions again a lot today. And we ended up with, if we encode our entire board, you just get this giant stack of zeros and ones. But this is like a really useful format for our AI to actually look at our chessboard. So then we got to kind of the fun part where we could get all our training data. And if you remember, the training data looks like this right here, where we have a chessboard specified in that Fed notation. And then we had a score for black and the best move. And we don't want to actually predict the best move directly. What we really want to do is we want to basically take the board and predict how good is this board for black. And you know that it's very easy to flip this around. If you just put a negative in front of black's score, it kind of becomes white's score. So we just want to build a model that takes in this board and predicts what is black's score going to be. So how good is this board state for black? So we wrote a few more sort of helper functions, and then we got to actually build our model. And we talked about how Keras is sort of this Lego set for machine learning, where they have all these little toys that you can plug together and make something happen. And so our sequential model takes in this flatten layer, which just says, okay, all of that sort of three-dimensional matrix you have, just squash it out to one single line of ones and zeros. Then we had a dense layer. Oh, hello. A dense layer that basically says, give me 128 neurons that are all connected to all of your inputs. And then all those 128 neurons all link up to the next layer that just has one output. And that one output will end up training to be our black score, right? Then we compile it with an optimizer and a loss function, which we talked a little bit about. And then we actually got to train. And so here we just trained for 20 epochs. And then we got to come down and look at our training loss. And so we're going to actually be diving into this graph of what training loss is and what it means. But one of the things we threw out is that this is actually a really nice looking graph. Our loss continually goes down. You remember our training loss is basically how well it does on, or I guess technically how bad it does on the data it's seen. And our validation loss is how well it does on data that we haven't seen yet. And so this is actually great because we actually do even better. Our loss is even lower on data we haven't seen than data we have seen. And that can be for a number of reasons. We might just have easier cases in our validation data set. But the big picture is that this is what we love to see. And we're going to try to purposefully make this graph look nasty by messing with our parameters. But generally we think that's pretty good. We like that. Then we looked at, now that we've built a value function, we looked at how do we turn this value function into a policy, right? And what it looks like is we just loop through all our legal moves, right? We encode them into our big vector of zeros and ones, and then we just run predict on all of those potential future worlds, right? So we just predict the value of all the possible worlds that we could go to by making a move, and we just see which possible world looks the best. And whatever world looks the best, we just play the move that gets us there. And so it's really pretty simple to turn our value function into a policy. Then we got to play against that with this play neural network function, and it wasn't perfect, but it was pretty good. We could pull it back up again and we could play it, we could revive it, but we won't because we have bigger, better things to do. The one thing we won't review this too much, but this notebook part 3 is sort of all that work we did in part 2 in building our model. How do we just turn that work into a submission to our competition, right? So all of this first cell here, all this code is just copied from part 2. And then, so there's the training. We saw we trained for a little bit longer and we got some different results here. You can see we still get better, but we don't get better quite as fast as we did up here. And then we basically applied our play function to all of our test cases. So remember our test DF, if you look up here, it has the same ID column and the same board, but it doesn't have a label over here. There's no label that says this is the right answer or this is the score. And so that's what we're trying to predict here. So we actually predict the best move because remember the thing that comes out of play neural network is the best move. And we can see that all of our best moves are in this notation of this is the starting square and this is the ending square, go do it. And then we actually wrote that out to a CSV to actually submit. And that's how we submitted, which, to just bring it back, if we go to the leaderboard and we see these scores, Yuri Moraz, shout out to Yuri, got more than a third of all of those cases predicted the exact correct best move, which is super dope. And I'm very proud of you, Yuri. Also shouts out to Checkmate and to Sai and to the other Sai, which may be the same Sai, I don't know, and Amelia and Platinum J. All shout outs, and Poya and Brady. Okay, everybody gets a shout out. You're all great. Incredible performance all around. So there were a couple things I wanted to dive into today, And the first one, just to get this out of the way, is training a model. So I want to, let's see, how do we want to do this? I think maybe I'll even actually, let's see, can I fork and edit this? Yes, so I can copy and edit my own notebook. And we will call this part 4. Call it part 4. Oh, hello. We'll call it training a big model and saving. So if you were here from last time, you remember that as our model got bigger, it just took more time to train, right? And this is pretty classic. This is like a big problem in machine learning is just like how many GPUs can you stack together and how long can you get them for to train a model? Because some of these models, if they're big and run on lots of data, they take months and months to train, right? I'm sure that GPT 3.5, GPT 4, these are I want to say in like the tens of thousands of GPU hours sort of range. So a lot of compute time that goes into them. And you would hate to, every time you wanted to use your model, have to retrain it, right? So it's really useful to have a sort of a system for being able to train it and then save that model and then come back to it later. And so let's see. And so why don't we do that? So we've copied sort of all of our core code over here. So we're hopefully familiar with all these. If you have any questions about the code in here, also, if you want to follow along, you can do this same, come over to this notebook. I'll paste that, and then just click copy and edit. Oh, it's kind of off screen there. But click copy and edit, and then you should be in the same place as me, and we can, we'll look at updating this. So we can start by, I'm going to scroll down here and find where we actually train our model, and I want to actually separate the training process. So all of this from training our model down, I'm going to cut that and then just paste it here. So the training happens later. But we can just run this cell. So this will do sort of all of our setup work, install everything we need, import stuff, define those functions that we worked with, and then build and compile our model. And it should take a second to get going. Oh, I guess we can keep this current by calling this part 4, training and saving a big model. So a couple of things to call out as this is running is, for starters, we have, I want to say, almost 80,000 rows in our training data set, but we're only using 20,000. We're only using essentially 25, like 1/4 of our overall data. And you can imagine that the more data we give our model, the better it's going to perform, right? It just has more examples to learn from. So we could, instead of, in order to sort of try to supercharge this, which is just installing a bunch of stuff right now, we could imagine bumping up the amount of data we're using. Instead of 20,000, what if we used 40,000? So we're making our training set twice as big. Let's see, polar void. Okay, this is a great question. And we live to get off topic here. Might be off topic, but how would you get it to think a few steps ahead? I'm guessing the best move right now may lead to a suboptimal one in the future. Yeah, so this is something that we sort of skimmed by this. But so the sort of classical way to play chess is, or to build a bot to play chess, is this thing called minimax, which is basically this idea of you look at all possible moves you could make, and that's, that like gives you 20 possible next boards. But then in each of those boards, you look at all the possible moves your opponent could make, and you repeat this process, right? And the problem with doing this process too much, so this is building a tree of all possible chess games, at least from this point over. The problem with doing this is this tree gets really, really big, really, really fast, right? So this is actually there's a program called Stockfish that does this, and you can do it pretty fast, right? But because that tree gets so big so fast, you can't go that deep. You can't go all the way to the end of the game, right? Because like ideally, you would just pick a set of moves that like guarantee that you can win, right? If you could go all the way to the end of the game, you could just think through all the way to the end of the game and always win if you found that right set of moves. That obviously is like computationally prohibitive, right? So usually what people do with chess engines is they actually specify a number of layers down to go. So you basically say, it's called max depth, and you could say 10. And so your chess engine will think up to 10 turns in advance. And there are a couple ways that it accomplishes this. One of them is with pruning. So if you, we could say that you need to check because hey, you might be able to say sacrifice a queen in order to put them in checkmate or whatever. This is sort of that you don't always want to do the greedy thing that looks good right now that might be worse later on. And this is a really great point. And so you might be able to not rule out all of those cases where something bad happens, you lose a piece, but there are maybe some places that it's like, okay, if the next two moves result in you losing your queen and both your rooks, like maybe there's still like a galaxy brain way to come back from that and win, but probably it's not the best sort of branch to explore, right? Anyway, this is the way that a sort of classical chess engine would do things. And basically what we're doing here is we are training our AI on what that process says. So it's not just saying, is this state of the board like good just this turn? But it's saying, hey, based on what this other guy said was going to be good 5 turns from now, is this good now? So it's a little bit brain bendy, but in theory, its notion of what a good board state is actually is thinking ahead a few turns in advance, right? So it's not just saying, do I have the most pieces right now? But it can actually, because it's being trained on this model that is thinking 7 turns ahead, it can actually have some sense of that. I don't know if that fully answers the question, but that's currently what we're working with. I did think about, maybe we should program that solution that does the, sort of the tree search, but I figured 7 years, yeah. But I figured this might be a little bit easier entry point into doing this process. Okay, so this should have run now, and we compiled our model, and we probably should have said model.summary to get a summary, although that actually might wind at us, never mind. We could just say, we can just say model, and this should run fast now because we've already installed stuff. Incredible. I'm glad that answered the question. And I'm glad you're here. It's good to see you. Also, you should totally enter the Kaggle competition, Alvin. It'll be a good time. Okay, so we beefed up the amount of data we're using. We're now using 40,000 instead of just 20,000. And then we can look at making our model even a little bit bigger too, right? So I think this was already a little bit bigger, but we could think about adding another layer to it. We could say, what about 64 neurons at the end of this? So this is actually, I think this is an interesting thing to your point at Polar Void. One of the things that is limiting our model's ability to really think 7 steps ahead is its architecture. Because right now we're just doing a single layer, and sure, there are maybe things that from a single dense layer it could actually see ahead, but you got to think that probably if it's going to notice these dynamics that are not direct, that are not just what's the line of sight of our queen, then it's going to need to be able to refer to other things and have a little bit more of an abstract notion about the chessboard. So maybe adding another layer will give it the ability to see some of those dynamics. So maybe we make it a little bit bigger. And then, so let's run that one last time, and we saw our model come out. And then what if we just set about and train it? And the big catch here is just that it's going to take a very long time to train. And we can actually just get rid of this play neural network function. I don't know if we want to play against this one. Hey, Alvin signing up. Feel like Alvin signed up for the competition. It's cool. Okay. Is thinking about it. Oh, okay, cool. Our first line here finished. And so now we can hit run here. And we'll get a sense. I might actually abort this if it looks like it's going to take too long. But okay, so if you remember from previous sessions, it took about like 20 seconds to finish our whole training process. And here, it's taken some time, right? It's not instantaneous, and it's not taking that long. But it would sure be a shame if we had to do this multiple times, right? Now, you could qualm and say, hey, like you could use GPU, and we could actually. I want to show you how to use the GPU on Kaggle, but the short answer is you just come up here and you pick one of the GPU options, and it will make things faster. But for the time being, I'm going to leave this training process to run, and I want to jump over and explore something else. So I want to explore this idea of overfitting. So we're actually going to copy this again because this has sort of our basic model in here. Oh wait, no, this is part 2. I really want to copy part 3, don't I? Let's go to part 3 and copy and edit this guy. And we'll call this part 5. Oh, hello. Overfitting. Okay, so just like before, I'm going to scroll down to, actually, I'm going to scroll down all the way, not all the way. Yeah, we'll grab our training section. So come all the way down here to the model.fit line, and we'll copy all this, and we will paste it down here. Cool. So what is overfitting? Here, I'll make my face big again. I think I run the risk of just being feeding a fed horse here and using my own analogy to death. But the analogy that I often will use for overfitting is this analogy of you taking a test, right? So say you're in a biology class and your teacher has a bank of questions, and she has 100 biology questions, right? And something she could do is she could just give you all of the questions with answers as a study guide, and then say, hey, 10 of these are going to be on the test, right? So you already see all of the questions. And one thing you could do is you could study it and you could learn biology really well, and then you could do well on the test, right? But something else you could do is you could just memorize the answers because you know that those questions are going to word for word be on the test, right? And that is ultimately something we don't want to do, because if that's what you did, if you just memorize the answers, then when you see a frog in the wild, you won't know what it is, right? You won't be able to generalize. And this is kind of what we call overfitting. And there are lots of ways that we try to sort of defend against it. One way that we simply just try to identify it is by having this sort of secret holdout set, like a test set. And so this would be the equivalent of your teacher basically picking 10 questions and hiding them, and then giving you the 90 remaining questions as your study guide. So in that case, the only thing that you can actually benefit from is from actually learning, because memorizing it won't actually help you on the test set. And so when we were training, we saw that validation line, and that validation line was going down. So that meant that we were actually learning things that were generalizing to data we hadn't seen before, to chessboards that we had never actually played, right? But so I want to actually try to push our model into a space of overfitting, just so we can see what that looks like, and of course look at how to prevent it. So we will go boom, part 5, overfitting, and we will, let's see. So to start back with our analogy. Oh, also actually, because Polar Void is here, one of Polar Void's analogies that I have used now, I've totally stolen, is just, or not really analogy, but more of a quip, is that when your model is overfitting, it kind of has conspiracy theory brain. It'll start like seeing these random things, and it's like, no, like, trust me, on the 3rd Tuesday of every month after a full moon, the answer is always C, or something, right? It'll come up with these ideas that like aren't actually true in general, they just happen to be true once. It'll start sort of really believing these coincidences. So how might our model, if we're thinking about trying to memorize a study guide, what would cause our model to start memorizing the data instead of actually learning it? Well, one option is the smaller your data set is, the easier it is just to memorize a few things. So one thing I want to do is let's make our data set just way smaller. Let's go down to 200 games. And we'll leave our validation set the same. That's fine for now. The other thing that will often lead to to this idea of overfitting is making a really, really big model. So the total number of neurons that we give our model, the more neurons it has, the easier it's going to be for that model to just memorize things. Actually, open question. Did anybody ever do this? Did anybody ever have a case where they just memorized the answers and they had a big enough brain with enough neurons to not actually learn anything, and they just memorized and regurgitated stuff? Let me know in the chat if that was you. It couldn't be me. Absolutely not. So how would we make this really big? I don't want to go crazy, but what if we just said, oh, excuse me. What if we just multiplied that by 4? We did 4096. Boom. So we have a lot of neurons and not that much data. And we will let that start up. Let's check back in our, this is when you know you're a real machine learning scientist, is when you have multiple jobs running at once. So we're still not done, right? We're still at 32 out of 40 epochs, 33. But in a second, we'll come back and we'll be able to save this model so we don't lose all of the hard work. So back on part 5 with overfitting. Oh, invalid syntax. Oh, I lost the comma. Okay, cool. Which actually, activation. Actually, maybe we just copy this or cut this and paste it below so we can run this. Sequential is not defined. So we need this as well then. And actually none of this run. That would be a shame. I guess if it's a syntax error, none of it would run, would it? Do we have any academic questions about overfit? If you have ever attended a Global Hack Week with me before, I have probably shouted at you about it. Cool. Which I guess to make things very topical and relevant, there are these cases where I'm sure you've heard of ChatGPT and these large language models hallucinating. And there are lots of reasons this can happen, but there is this really, really common case of like there was some specific text in its training data, and like it just think that text needs to come out, and so it ends up sort of regurgitating that. And that is like a classic example of overfitting. There was, I think it was like some username that had Magikarp in it. It's like a Reddit username that ended up in the training data, and whenever it saw that username, it just like went absolutely nuts because it was like, oh, I've seen this specific thing. The thing that needs to come after this is like all of this random garbage. So this is a case where this large language model had in fact overfit on its training data. Okay, so we build a really giant guy, and then we can delete this, but let's just run this and see. This should be fast because we don't have that much data. Yeah, so this is pretty quick. Okay, great question. Does using power of 2s for the layers improve performance? And the answer is sometimes. It depends. But often, if you don't want to fully think through it, you just pick a power of 2, just because you might get a speed up. Generally, the answer here is that specifically if you're running on a GPU, which currently we are not, but if you're running on a GPU, that having sort of your batches of data, so we'll feed the data into our model in these batches. Having those batches conform to these nice power of 2s sometimes can get you efficiencies in going into the GPU. So the answer is like often, and we often pick powers of 2 just for the chance that we might see that sort of improvement. Okay, so we have not technically gotten to overfit yet. You can see our validation loss is still, I mean, it's getting a little bit funkier, but it's still above, or it's still like not much higher than our training loss. So one thing we can do is just let it train for longer. We can check that. That'd be interesting to see. I also want to double check to make sure. Yeah, okay. So we're using the first 200 rows for training, and then the last 1,000 rows for validation. Cool. And that still should be pretty fast. Alan's problem with ChatGPT is that sometimes it writes almost correct stuff that looks legit. Okay, this is actually, while this is training, this is going to be, I think, a separate little, an aside. So there is, I'm sure many folks are aware of this term, but there is this term called alignment, which is this area of research, which is sort of how do you make sure the thing that you want is the thing that this AI system wants, right? And there are lots of ways that we go about like getting our AI misaligned from the things that we actually want. Like a classic example is like, oh, you train it on a bunch of racist data and like you're not racist, but like then the model ends up saying a bunch of racist stuff. That one is like, I mean, obviously still terrible, but like an easier one conceptually to fix. You just filter out all the racist data that you trained it on and it should, that should fix it, right? But there's this other issue with the way that a lot of these LLMs are now trained is something called reinforcement learning with human feedback. And the idea is whenever you use ChatGPT and you give it a thumbs up or a thumbs down, that actually goes into the system to train the next version, right? That now actually lets the model say, oh, the human liked that, right? And on the one hand, that seems great, right? We want the model to sort of do what we want, and we want it to be responsive to human needs. So like, why not make it want that thumbs up, right? But the problem, and I think this is actually like very likely related to this problem that you're mentioning, Polar Void, is the issue where when it's trying to get your thumbs up and that's its metric of success, then think about the scenario where it doesn't know the answer, right? You're asking it for some information that just was not in its training set, it doesn't know, and it has two options. One, it can say, I don't know, which is true and is correct, but it's never going to get you a thumbs up, right? Like that's probably going to get you a thumbs down for not knowing, or you can lie about it. And if you lie about it, one of two things happens. Either you lie about it and the human knows you're lying, in which case, oh yeah, big thumbs down, or you lie about it and the human doesn't know, right? And so in case number one, where you are honest and you say, I don't know, you definitely get a thumbs down. But if you lie, there's a chance, if you lie when the human doesn't know the right answer, there is a chance that you get a thumbs up, right? And so this is basically the thing that we have actually told the AI to do is only lie about things when you think you can get away with it, right? And that is just like, I think, kind of funny, but honestly terrifying as like an issue. Yeah, it's kind of ridiculous. But so alignment research is really important, and I think it is. I mean, it's a real limitation with currently the sort of state of the art on how we train these models. Okay, did we get some overfitting? And this is interesting. We've still not overfit. We've still gotten. I mean, as you can see, like certainly our validation loss gets like weirder, but let's see. What could we do? I mean, I suppose one option, because we're just really trying to force this model into failure now, right? We could give it even less training data, like as to a point of almost being comical. We could give that a shot. So now we're saying just from 20 chessboards, we're going to see how much you can learn. And that comes out to train DF becomes xtrain. Cool. So let's build our model again, and let's let her rip. Which we probably don't need actually. We don't need 100 epics for this. Like hopefully this should do something in 50 epics. That is so interesting. Our validation loss is still pretty low. Yeah, this is super, super interesting. Well, what if we did go up to 100? We might also think about making our model deeper. Okay. So this gets tricky because, well, for a number of reasons, but it just gets very small and our scale gets a little bit, we broke chess. Is chess actually really easy? Is this what we learned? It's really difficult to overfit on chess? I guess the other thing to throw out is talking about alignment. Technically what we are training our model to do right now is to predict like how good a board state is. But this doesn't actually necessarily mean it's going to make a good move, right? Like this is actually, we're using one metric as our loss, which is, how good is the board state? But that is a different metric than did you play a good game of chess? Did you come up with optimal moves? So I think an important thing to sort of highlight there. But okay, what if I want to run for 200 epochs, and then we're going to cut off the beginning of the plot. So we will just plot, let's say, 100 to the end. So we'll do it for 200 epochs, but we'll only look at the last 100 epochs. So hopefully that'll let us zoom in a way that's helpful. We could, of course, try to train on one sample, and that should be wild. That should be ridiculous. But I think you'd really need to train on 2 samples just for it to mean anything, you know? But we could try 2 samples. Which I think this is actually an interesting exploration into what is our model learning. And so if you are, we can just step back into sort of chess corner for a second. There are a couple different ways that you could think about, like levels that you could evaluate a board on, right? Sort of the first one, and we're going to use this later, but the first one that we might throw out is the idea of counting pieces of material, right? This is the idea that some of your pieces are worth more than others, and you can add up all of their points and kind of see where you stand, right? So we usually say a pawn is worth 1, bishops and knights are worth 3, rooks are worth 5, queens are worth 9. And so you can just add up all those numbers, and your king is kind of worth like 0/infinity. You know, you can't lose your king. So all your other pieces just count material. And so, like, on the one hand, like, probably the first thing that our model has to learn to know how good a board state is to count pieces of material, right? And that's something that probably actually you don't need much data to get a good sense of. Then, if you're going to think about the next sort of layer to this, like what next thing would be useful to learn, there are some sort of vague strategy things. Like we throw out this idea that you want to control the center of the board. So, you know, a queen in the corner is maybe worth 9 points of material, but a queen in the very center is probably more powerful than that queen in the corner. So, you know, maybe you get some vague sense of, okay, position kind of matters. And then after that, then you suddenly get into this world of, like, well, what pieces are threatening which other pieces, right? Like what pieces could on the next turn or 3 turns from now take another piece. And that suddenly, I think, becomes a much harder thing to learn. So if I had a hypothesis for why this is behaving this way, is that you can still actually get pretty good behavior. Oh, wow, okay, this is going to be a good graph to see. It's kind of psychedelic, actually. Let's see. Okay, boom. Look at that. Isn't that nuts? Which, I don't know, this now has me concerned that, like, that looks like a little bit too in sync. And it makes me wonder if we might actually be testing on the same data that we're training on. But no, we do have ValDF. And ValDF is a separate slice. Okay, just because I don't want to be crazy, I just want to double check. What is our first Y train? Actually, this isn't actually going to be that helpful. Let's see. Or do we have train DF? Yeah, okay, we have train DF and then val DF. Okay, what does train DF head look like? And then I just want to double check that val DF is in fact different. And they're not different. Aha. Okay, we debugged it. This is why things are not actually looking like we expect them to be. So we're actually testing it on the same data that we're training. This is sort of the classic example that we threw out. This is when your teacher gives you the actual answers to the test as a study guide. So why is this? I guess. Oh, do I need to be doing like .iloc? Okay, let's try this. So I believe just the indexing like that isn't going to work. I think if we do something like this. Okay, yeah. I think I need to change how I'm indexing, and then we should be off to the races. Oh my goodness, you're so right. You are so correct. That's so embarrassing. Okay, so we gotta get ValDF first, and then train DF, which honestly I should just have better variable names. Yeah, no, that was pretty embarrassing. But this should be okay. You can check my work, but I think this should be okay. Really, we should just have better variable names, but I can't be bothered right now. And now I feel like we're going a little bit extreme. 200 cases, that's still probably fine. Okay. No, honestly, I should have known that those lost graphs were kind of funky. They did not look right. Okay, cool. And I don't think we'll need 200 epics. Honestly, I think 50 should be enough. But hey, honestly, Alvin, it wouldn't be a global hack week if you didn't point out a bug in my code. I feel like that's the dynamic we have, right? No, I think we didn't break chess. I think chess remains unbroken. And okay, now my graphing is wrong. Honestly, that was fast enough. Let's just run it again. Okay. Now we're getting somewhere, y'all. Now we're getting somewhere. That wasn't even a good bug. That was a silly bug. Okay, this is what I like to see. This is what I'm talking about. So you can see our valid loss is just way up here, which in fact we could even make this a little bit more sane. We could give ourselves more training data. Let's give ourselves at least 1,000 records to train on. So hopefully we can learn something. But in fact, we probably don't even need to make this model that big. Let's go back to 1024. So we're going to make our model a little bit smaller, and we're going to hopefully still trains pretty fast, but hopefully see a slightly less depressing outcome. But this is science, y'all. You make some mistakes, you're gonna learn some stuff. You're going to, as they say, fuck around and find out. Okay, cool. This is a great graph. This graph works for us, right? So you can see, so this is how we did on stuff we hadn't seen yet. And this is how we did on stuff that we had seen, right? And you see, we keep doing better at the stuff we've already seen, but we don't actually get that far. We only, up to this point, we actually are doing a little bit better. We're learning something, and then we just kind of go into chaos, right? So right around our 10th epic, that is where we stop actually benefiting from training. As long as you measure the result, it's an experiment. Yes, this is, my boyfriend and I have gotten in this habit of having a spreadsheet for anything we experience. So we have a spreadsheet for movies, we have a spreadsheet for meals, we have a spreadsheet for wines, and after we experience one of these things, we'll give it ratings, and that makes everything science. So, do we have any questions about what's going on here? There's a point where we're actually learning stuff and it's actually generalizing, and our validation loss is getting lower. And then from here on out, all this stuff that we're learning is helping us only on stuff that we've seen before, and it's not actually helping us on stuff we haven't seen. So how do we avoid this? Well, you got a couple dials to turn, and we will turn them all in order. So the first thing you could do is you could just make your model a little bit smaller, right? You kind of need a big brain in order to really memorize stuff. So what if we just cut the brain down from 1,000 neurons to 500 neurons? Now let's run this again, still for 50 epics, and let's see what happens. And we'll see if we get better. Why are we doing so bad? Yeah, well, I mean, to be fair, we just have a very, very small training set right now. And honestly, that testing on our training data gave us unrealistic expectations about how well we do at chess. Are we gonna get some graphs? Boom. Okay. So you can actually see we're doing a little bit better here, right? It used to be that only the first 10 epics were really useful to us, but now really probably up until the 20th epic, it's actually kind of useful. We're still doing a little bit better. And then things get a little bit pointless, right? Another thing that we can do is add something called dropout. I don't actually know how useful dropout will be on this problem, but we can give it a shot. So dropout, we can import this as a layer. And you just pass in a percentage. And this percentage is basically how fuzzy do you make your data. So dropout basically says we're going to randomly drop a few of our neurons. And there are, it's an interesting sort of academic topic of why this works. But so you could say 0.2 and say we're just going to fuzz it like 20%. So there's a 20% chance that any given neuron just like doesn't work this turn. And so a lot of interesting thoughts about why this works. It tends to make your representations of things sort of more distributed. So if you can't rely on any individual neuron, then maybe you can't like just memorize that one specific pattern because it might be fuzzy next time, right? So maybe this forces you. This is kind of like the maybe the example of dropout is if your teacher would change the numbers if it was like a math problem and the question would be the same, but they would just shift the number in the math problem. Maybe that's like dropout, where like it's going to be fudged a little bit when you see it again. And okay, yeah. Like I would say probably that helped a little bit. Not much, but a little bit. You can see that we probably get some gain all the way out until like maybe the 25th epoch. So more training is still useful a little bit further out. But then we come to sort of the big one. And this is like the sort of the king of, of the past decade of machine learning is like, well, what if we just had more data, right? And we were arbitrarily limiting ourselves to, we did 1,000, but there's no reason we couldn't just kick it back up to like 10,000. Let's give ourselves some more data. Polaroid said, would stacking layers help? Yeah, so this is a great question. So generally speaking, if you you need a lot of data in order to be able to train depth. Usually you can add some width, you can add some additional neurons on a given layer without too much data and like still have them be kind of useful as long as you're not overfitting. But you need lots of data in order to train additional layers. And this is something that we could totally try, but you don't want to build a model that's too deep when you only have like 1,000 records to train it on, right? So this will probably take a decently longer chunk of time to train, but we should hopefully get some better results. Okay, so now I want to actually pop back over. We're kind of doing the Martha Stewart, like you put a cake in the oven and then you immediately pull it out because it was waiting for you and you had prepared it before. And we have prepared this model before now. Obviously, we can't trust our loss numbers at all, or our validation loss at all. But what we can do is we can save this model and use it later, right? So something that we could do, this is just me juggling some tabs, is we have our model, boom, and we can say model.save. And we can pass in /caggle/working/saved model. Boom. And that, not sav, save. Boom. And we can, in fact, delete the rest of these, I think. Yeah, let's clear out the rest of this stuff. Delete cells. And we have saved a model. And you can click this little arrow here to see your working directory. And we'll have to load it, I guess. Boom. So we have a directory called saved model. And if it will show us, there are a bunch of files in here that specify exactly what our model is up to. Come on, Mr. Model. Okay, great. So we have our variables, our assets, our fingerprint, our metadata, and our saved model weights, which are lovely. And so if we want to actually use this in another notebook, this line right here, this is like learning about carrots. But the learning about Kaggle part of this is that if we want to use this in the future, then we have to come up here and say save version. So you could say save and run all. And you can even pick like if you want to do it with an accelerator. We can click save. And now it's going to queue up this notebook to run one last time. You can see it over here. And then from then on out, that output will be saved and we can use it in another notebook later. So we'll let that run and then we'll see how we can actually use that in the future. Great. All right, let's come back over to overfitting. And okay, cool. So now that we've added a lot more data, we get, I'd say, a lot more interesting curve and one that's not as depressing, right? So if you remember earlier, I think that our validation loss was bottoming out around 14 or 1500. And now, just with the addition of more data, we get our validation loss all the way inching close to like, what is this? Is that 100,000? Close to 100,000. And you can imagine, based on those trends, we should actually be able to train this more and get more juice out of it, right? We should actually be able to just throw some more compute at this and do better. But so that is our little exploration into overfitting. That is, I think, all we need to do on overfitting. And we have about an hour left, which I think we're going to use to see if we can do some ensemble models. So, what are we gonna do? So let's do this. Let's come back to our competition. I will drop that link in the chat again. Let's see, has anyone submitted? Do we still have? I think we maybe had 13 last time. I don't know if we got a submission. So let's go back to part 3 and copy and edit. And now we can call this, I guess this is part 6. We got a lot of parts. We'll call this ensemble models. Boom. So as I threw out, this idea of ensemble models is there are lots of kind of individual kinds of problems in chess. And one way that we break up the problem of chess is into an opening, a mid-game, and an end game. And the idea is when there are fewer pieces on the board, you kind of start worrying about different things, right? In a mid-game, you're kind of really interested in the strategy of like, okay, do I control the center? How is my pawn structure? But by the end game, you are really looking at like, okay, what next 3 turns can I put them in check with, right? You sort of get a lot more tactical about, well, what is this one piece going to be doing 2 turns from now? And so one thing you can imagine is that having separate models that specialize in these different areas could be useful. So one thing that we can try, we can, I guess, again, let's roll down here and, yeah, let's actually, everything from pandas we can copy or cut and paste. Boom, let's cut all that. We can run this. So this will just define all of our little helper functions for us. And then sort of all the quote unquote real machine learning will happen below. Also pausing to stay hydrated and see if we have any questions. Is everyone feeling good about this? Right on. Our session has started. Polar Void's feeling good about it. We love to see that. Boom. Okay. Oh, and actually, maybe we can close out our training a big model and saving it by actually sharing it. So right now, there are the only notebooks part of this conversation, or as part of this competition are mine. And somebody who writes a notebook and publishes it is going to get swag dropped, and it could be you just by copying and pasting the same thing. So we can come up here and share, and you can make it public. And if you do this, then it should show up in our competition. So if we come over to our competition and we go to code, mine should now show up. Boom. Part 4 is now here. So if anybody else does that process, then you will have submitted a notebook. Yeah, it's a good question. It's a little more quiet. I would say I think that this as a global hack week has just been a little bit more low key. I know it's like kind of around exam season, so I imagine that probably has an impact on it. But yeah, it's also actually this time I'm doing something weird where technically train an AI to play chess is not its own track because I'm only doing 2 sessions, and generally tracks have 3 or 4 or 5 sessions. But I was like, you know what, I think this will be fun, and I only think there are really 2 sessions here. And Mary was like, yeah, sounds good. So we just had one other session at the beginning of the week, which that one was a little bit better attended. I think we had maybe 30, 35 folks sort of joining the live stream. Right on. Okay. So we learned how to publish a model. Give me a thumbs up if you learned how to publish a notebook. And if anybody publishes a notebook, I will give you an upvote. I'll just smash that upvote button, y'all. So we saved a model, which is great. And now let's get back into ensembles. Okay, so we've done our we've introduced our helper functions here. And now we want to read our data. Oh wait, did I not paste the code? Okay, great. So we pasted all the additional code there. And so what I want to do, so let's import our data. We'll bring this up into its own cell. But actually, let's look at what our data says. So in our data, we have all of these chessboards. Thank you for the thumbs up. I appreciate it. So in our data, we have all these chessboards. And so if we want to train a model to specialize in just the mid game or just the end game, or just the opening for that matter, how would we go about doing this? Well, one thing we could imagine is writing a function to count up pieces of material and then to use that number of how many pieces of material are left to sort of just categorize it as, okay, if there's a lot of material left, then maybe we think, yeah, that's probably still the opening. If there's a little bit of material left, then maybe that's the mid game. And if you have a very small total number of pieces left on the board, then maybe we say, yeah, that's probably the end game, right? So let's write that function that just accepts a chessboard and returns a count of the sort of total pieces of material left. So we can say def count material, and we'll accept a fen board notation. So I think the first thing that we have to do is we just have to make a dictionary of all of the pieces and their material values. So I kind of know it by heart, but we could pull up, let's see, material value of chess pieces. And we should just have a table somewhere. Okay, boom. Oh, that's not what I meant to do. So if we zoom in, you can see we have a pawn is worth 1, a knight is worth 3, a bishop is worth 3, a rook is worth 5, and a queen is worth 5. So we can come over here and we can make a material dictionary. And we can just in here put a P for pawn is 1 point, a B for bishop is 3 points, an N for knight is 3 points, an R for rook is 5 points, and the Q for queen is 9 points. And then we can basically loop through our fen. So we could say for character in our fen, we could basically say if our character is in our material dict, which really we should say dot lower, because for white, all these letters will be uppercase. Oh my goodness. So the queen is a material girl. Yes, I would say this comment deserves an award. The queen is a material girl. So we will iterate through our fen, and for every character, if that character is indeed a piece, so if that character is a piece in our dictionary, then we'll say we'll initialize our total material as 0. And every time we pass it, we will just add whatever the value of that piece is to our total count, and then we can just return our total material. And so now we can just take our training dictionary and we can just say total material is equal to, let's see, train df board. And we'll say dot apply. And so this will basically run our count material function on all of the boards in our data set and then return the output of that to this column called total material. So we should run that, and it should run pretty quickly. And now we can import matplotlib and actually plot a histogram of all of our values. Because we can just look at our total material, but it's not going to actually tell us that much, right? Like, okay, yeah, we have some numbers, but what's a normal chessboard? So we can say plt.histogram and just pass in our list of total materials. And so this is like all these different chessboards, like what's a typical value for how many points of material are left on there. And this, I think, is super interesting. I think this is cool. So we have this, this pattern where in a lot of cases, we have maybe 20 points of material left. But in some cases, we have all the way up to like 100 points of material left. And you could ask, I want to say that each side starts with around 40 pieces of material. And you could ask, like, wait, if each side starts with 40, how could there ever be more than 80 pieces of material on the board? And the answer is through promotion. So if you get your pawn all the way to the end of the chessboard, to your opponent's end of the chessboard, then you can turn that pawn into any piece you like, which in practice, it basically always is a queen, right? There are maybe some rare cases where you want to turn it into a knight, but usually people turn it into a queen. And so suddenly, you have just added 8 points of material to the board, going from a pawn that's worth 1 to a queen that's worth 9. So you can imagine if you get 3 pawns to the end of the board, even if a lot of pieces have been taken off, suddenly that is still like a really high point of material board, which that's an interesting case where maybe our metric isn't great, because that's a case where you're probably actually pretty close to the end game. So many material girls, so true. You're pretty close to the end game. So maybe that's a way in which our metric isn't perfect. But so we get this general idea of the number of points of material on the board will range from, at the low end, 0, to at the high end, 100, right? So maybe we could just, if we were going to try to draw some boundaries around this, maybe we could say, hey, if you have greater than 60, then maybe that's an opening. And if you have between 30 and 60, maybe that's mid-game. And if you have less than 30, maybe that's an end game. So we can actually just break up our data set into individual parts in order to give ourselves some end game examples, some mid game examples, and some opening examples. Ribslinger, Kaggle, are you a Kaggle fan? Because I'm a Kaggle fan, and it's great to have you here on stream. Boom. If you are interested in joining along, I will go ahead and drop the link to our competition. Good. But yeah, shouts out to Ribslinger. Good. Okay, so we have kind of picked these thresholds of, hey, if you have more than 30 pieces of material, or if you have less than 30 pieces of material, then you're in end game. If you have more than 60 pieces of material, then you're in opening. And if you have in between, then we'll call that the mid game. So let's take our training DF and split it up. So one way we could do this is we could just say when our training DF total material, I guess for starters, you can take a column and you can compare it to something. So let's say greater than 30. And this gives you a bunch of trues or falses. And so what you can turn this into is, this is basically, well, is this row part of the end game? Or I guess we'd really say if it's less than 30, then it's part of the end game, right? So we could say that all of these, where these cases are true, that's end game material. So we can just say train df of those true cases, and we could even call this our end game df. Maybe we should actually look at it. And cool, you can see that all of these cases that we pulled out here have less than 30 points of material. So now we could create a mid-game, which would be where the pieces of material are between 30 and, I think we said 60. And I think in order to make this happen, we'll have to do, we could say greater than or equal to 30. And then I believe this is where we whip out our AND operator, and we say that total material is less than or equal to 60. And let's make sure our mid-game DF looks reasonable there. Oh no, it's not an AND here. You need to throw in some parentheses to make these set expressions. There we go. Okay, so you can see now all of our points of material are between 30 and 60 for our mid-game. And then we can just finish off with our opening, which is any case that has greater than 60. So if you have, if your total material left on the board is greater than 60, then we'll call that end game, not mid game. So if we're actually going to train our model on this now, what we actually want to do is generate 3 individual models. And so the first thing that I'd do is I would actually split all of these into a validation and a training one. I named one wrong. What did I name wrong? Or is this just a delay from what I named? Oh, wait, yeah, no, I named it end game again. Technically, this is opening, isn't it? It's, yeah, if you have more than 60 pieces or more than 60 points of material left on the board, then that we'll say is an opening. We have these 3 different segments of the game that we want to train 3 different models on. And so the first thing that we might do is we could do the same split up where we grab a bit of data for validation and then a lot of data for training. So we could say end game val df. We could say is maybe the last 1,000. The last 1,000 records in our end game, and then we could say our train DF is everything but the last 1,000. We could do sort of the same thing with mid game. Let's see, what's the easiest way? We're gonna copy and paste this. Replace this with mid game. So each of our sort of phases of the game, we're splitting up into 2 pieces. One for training, one for testing. And then if we come down here, we'll actually want to grab this little transformation here where we actually turn them into the encoded states. We'll need to do this for each of our phases. So maybe, oh, did we not actually create our opening DF? There we go. So split each phase of the game into a training and a validation set. It's into training and validation sets. Boom. And now for each of those, we have validation and training, and we want to turn those into those vectors, right? So this is going from, we just have the nice little string. Like if we look inside what our endgame DF looks like, we have all of this data. We want to turn that into just our giant matrix of zeros and ones, so our AI can actually really use that, right? So I guess let's go ahead and say, we can say X endgame train and use our endgame train DF. And then we'll have Y endgame train. And then we'll use our score for our endgame train DF. So this is all just processing the thing we're predicting with and then the thing we want to predict. So we're predicting from the board state, and the thing we want to predict is the score, right? And so that was for training, and we can do the same thing for validation. And we'll use the endgame val df. And we'll do this same thing for, so we'll prepare endgame data, prepare mid-game data, which will be the same thing here, but just with mid-game. Maybe we can do some copy pasta. Mid-game. Boom. You end up, I'm copying and pasting enough that at this point I'm like, should I have made this like a list of things and then iterated over it? Maybe I should have, but we're too deep now. We're just gonna continue down this route of copying and pasting. And then finally, we can prepare the opening data, which will be, again, the same thing, just using our opening data. It's really kind of nice that opening, mid-game, and end-game are all 7 characters long. That's really pleasing to my brain. So we have split our data up into these 3 different groups, and we have processed them all separately. This actually should take a second to run. Oh no, encode fen string. Oh yeah, that's a new little function we defined. So let's run that. That should be good now. Does it not let you have multiple cursors? Multiple cursors like mouse cursors? Or like cursors into data? I might not fully understand your question. Or is this like multiple people editing the same thing at once? Oh, like alt click or something. Yeah, it's a question. So you can right click and get all that stuff, and then you can, or for me left click here, and it's fine. But I assume this is like a question about like the Kaggle interface, which I would say in general, I think the Kaggle notebooks I think are pretty nice. I think specifically the feature of being able to just schedule them to run and let them sort of run permanently is nice. So I will say I'm on a MacBook, so I don't have like an Alt key. I have an Option key, which does something different. Yeah, no, I'm a peasant over here with my MacBook, you know. Okay, cool. So something that I should be able to do, which I don't know if I can here, is like search and replace all or whatever, which would be nice in this scenario. So we have prepared all of our data, and now we get to do the fun work of actually building 3 different models and training 3 different models, right? So here I might actually, what if we actually did do this in a loop? So what if we said for phase in, and we'll have a list of opening, mid-game, end-game. Oh, actually, maybe this is not what we want to do. I kind of would already need this in a dictionary, wouldn't I? We could. No, it's fine. It's fine. Okay, so let's build 3 models. So we can grab from down here. We can grab our Keras imports, and we want to create an endgame model. Is this confusing that I'm going in reverse order, starting with endgame? And we can just grab like basically this model. But the idea is maybe if our models are a little bit specialized, maybe they don't have to be quite as big, right? Maybe they can be a little bit smaller. So maybe we make this only 512 parameters, and we call this our endgame model. And we can basically, for all of these, or we can make 3 models. So we have our endgame model, our midgame model, and then finally our opening model. And we want all these to basically be identical, right? What if you make a function to do it and just pass it in each one? Like a function to do the training, or like a function to do like the whole, like this whole process? Because I could be open to either, actually. Maybe it'd be fun to do. We have 40 minutes. We could refactor this into one giant function where you just pass in the data. I like that. Let's do it. Okay. One function to rule them all. So we'll say def generate model. So this will just spit out a model that does the right thing. And all it will take in is data to train on. Boom. So this will take into data to train on. We will do our own splitting of this. I should have done this from the beginning. Yeah. Hindsight's 2020. And now we don't even need to give them special names. And we'll prepare it. Yeah, for sure. It was getting a little bit unwieldy. And we can get rid of all the endgame mentions. I feel like mentioning endgame so much, there are two obvious cultural references. One is the Taylor Swift song Endgame, which I think is a great song. And there's the Marvel movie. And I'm curious if anybody has any strong feelings about either the Taylor Swift song Endgame or the Marvel movie Endgame. Hello, curious one. Welcome, welcome. So we are just in the process of trying to build this ensemble model and sort of starting by refactoring how to build a model into a single function, right? So we have all this. We'll generate a model. And then we will compile that model, which we can grab our compilation code from down here. And actually, we can grab all this. And we'll just put all of this in there, and the function itself will spit out a nice looking graph. And then we get our model out. Boom. Curious one downloaded Twitch today. Very exciting. Well, welcome, welcome. It's great to have you here. Polar Void said you missed the first two end games. So I did. Which really, this should all just be data to train on. Boom. And that should be just peachy. So now all this actually works just fine. 40 epochs is probably fine. Everything there is named correctly. We'll print out our graph, and then we'll just return the model. Okay, this is great. Honestly, hats off to Polar Void. Always bringing some good suggestions, good ideas. 10 out of 10. So we could just delete this whole cell now. Delete cell, boom. Curious what it says. So can you tell me how things work around here? Yeah, so this is a great question. So you're kind of in the middle of a stream here, but the orientation is we are in the middle of Global Hack Week. We are doing lots of different sessions on different sort of game-related tech topics. And so in this stream, we are learning how to build an AI model to play chess. And so I will drop the link for our Kaggle competition, is where most of our sort of resources are. But if you go, boom, if you go to this link, the three things that I would point you to is we have a part 1, a part 2, and a part 3 all here that all sort of walk you through sort of the early steps of what we're doing here. But I'm glad you're enjoying yourself. And if you have any other questions, just jump in for sure. Incredible. Okay, so we have a cute little function that will just spit out a model for us when we give it some data. And we should now be able to run, here we can delete that as well. We should now be able to run that function on our 3 splits of data that we came up with, our endgame DF, our midgame DF, and our opening DF. And so now we can say our endgame model is equal to generate model, where we feed it in our endgame, we call it endgame DF. And this should actually print out all of the training and graph some stuff. Will I need to run the encode fen string block? I think I would have to if I didn't already run it again, but we will see. I know I didn't rerun it after pasting it. Oh, sequential is not defined. Checkmate. Not the errors I was expecting. Where is our Oh, did we delete our Keras imports? Okay, we'll say from TensorFlow dot, what is it? TensorFlow dot Keras dot models import sequential. We can be actually knowing the import statements, and then we can import from layers. We can import dense and flatten. And let's see if that does what we need to do. And hopefully we'll get a graph out of this. Why do we need to re-import them if we've already done it before? Yeah, that's a good question. I actually am not sure. I'm not sure why. Unless I think we actually never ran the cell. So previously I'd run the cell with this, and then I just copied it and moved it around. But I think I never actually ran the cell that imported that. Okay, so we're off to the races, and we are streaming. And we are training. We are also streaming. I guess I'm streaming. And we're progressing. Honestly, 40 epochs was kind of a lot given the size of our model. Maybe, should I abort and make it small? Yeah, if we're doing this for all three, maybe we should. Okay, we're gonna kill it, and we're gonna do just for the speed of us doing this, we'll just do it 20 epochs. Yeah, curious one. I would ask definitely like what are you interested in? Because I know a lot of the streams this week are more game related. We're obviously doing like machine learning here, but it is a great place to make some internet friends. I would say that definitely joining a guild, I feel like is the party line on how to make friends at Global Hack Week, which we can just drop. Let's see, guilds. Boom. Polar Void, are you part of any guilds? Bahaj Gang. There you go. Machine learning and also history. Yes, I think I am part of Blaj Gang. I'm not like super devoted, but I'm not part of any other guild, and I do know a lot of Blahaj gangers. This is fun. A thing that I'm working on right now is generating a data set to test AIs on their knowledge of history, which I think might actually be a future Global Hack Week. Okay, so we've trained our endgame model, which is great. And wait, did we do the same problem with validation loss? Because that looks too good. That looks suspiciously good. We have xval and yval. We broke chess part 2. Data to train on. We grabbed the last 1,000. And then, I think, I don't know. Now this is the same problem of like, well, I don't know. Like, it's not supposed to be, but, oh yeah, I guess if these were really small. But I think we chunked it so that they all should look pretty similar. And actually, no, with our indexing, I think we should be fine. But okay, let's see. We ran this on endgame DF, and we got the last 1,000, and then we also got everything but the last 1,000. Yeah, okay, so those are different. You can, I mean, it is also like plausible that we do actually just have some sort of quote unquote easier easier chessboards in there. Good deal. So we have trained our end game model, and now we could very, very quickly do the same thing to train a mid game model on our mid game DF. And we can do the same thing with an opening model on our opening DF. It's time to make clickbaity YouTube thumbnails. Yeah, I respect the hustle of people that can do the, you know, like the IRS cuts my hair. What? Like, I don't know. Things that are like I literally almost died at the post office. I guess ours would be today we break chess. What? How does that work? And we are training, and we are training. And maybe while we do that, maybe we jump ahead and look at how are we actually going to use this model. So I'm going to delete a lot of this code. But then our play neural network function, we're actually going to want to update, right? Because now we don't have just one model. We have 3 different models, right? So we have, so to recap, originally the thing that we were doing with our play neural network function was to take all of the board, take the board state, look at all the legal moves, and then generate what the board would look like if we did each of those moves individually, and use our neural network to rate them, right? And none of that has changed. The only thing that has changed is what neural network we want to use depends on how many pieces of material are left in the board. So we could just go up and, oh, okay, great. This looks good. And notably, you can see that our validation loss does actually get worse. So that's like a nice mental check that, okay, yeah, we're not like our first one did seem like pretty decent, but we're probably not doing anything funky. And the longer you train, the more likely you are to get a little bit of overfitting. But that's totally manageable in terms of how much you're overfitting. Which I think another thing that's interesting to compare, if we come back here, when we were working on sort of this general problem, when our problem was all of chess, I think here we had a bigger model and more data, but our validation score, we only get down to like, you know, about 100,000. But here, we get actually lower than 100,000 in way fewer, way fewer epochs, right? This is only 20 epochs. And back here, we took 50 epochs. So we get there faster. And I mean, technically our validation loss is even lower than that, right? So with less data and a smaller model, just by sort of segmenting our problem a little bit smarter, we got better performance. Same thing on the mid game here. We actually get way better performance faster with a smaller model, just by sort of chopping our problem up into smaller pieces. Let's see. Polar Void says, I know you have nothing to do with it, I think, but why do I get Russian Amazon and flower shop ads? That is a good question. Yeah, I will say I don't have anything to do with it. I don't know. I don't know if you're doing sus things online that make people think that you're into Russian Amazon and flower shops. Oh, this is on YouTube. Yeah, that's a good question. I mean, I think the thing that I will say, and many people have commented on the quality of ads, maybe not getting worse, but like getting weirder recently. And I believe this actually is a function of, you know, macroeconomically, we're in a little bit of a downturn, which means that on average, the cost of just putting out any ad has gone down a little bit. And when ads were expensive, because there's just fewer people spending money on ads because they're cheaper, when they were expensive, you like only had pretty well-funded companies, like comparatively spending money on ads, right? So you get ads for, you know, for Nike and for like, you know, for Louis Vuitton or whatever. But then as the price of an ad goes down, you get these just kind of weirder things that are like, well, hey, if the ad is cheap, like why not just throw our ad out there? And so I think that's why you end up seeing sort of more bizarre ads during economic downturns, because it's just cheap to put those ads out there. This is my theory. I don't know you in particular why you're seeing those ads though. Okay, so our model here. Okay, and we get incredible training loss in our opening. Look at that. We get really, really good, really fast training our opening model. So we can create our play neural network function, and the only thing that we want to do here is basically swap out what model we use depending on which phase of the game we're in. So we have our, what was it, total material? Was it count material or was it total material? Count material. So we can use this count material function on our current board. And we can basically say if material is greater than, or I guess if material is less than 30, then we can say model equals endgame model. Elif material is less than 60, we can say model equals mid-game model. And then finally, if we're in an opening, you can say model equals opening model. So we're just swapping what model we're using based on how many pieces are left on the board, and then we should be able to make our prediction like normal. We're just changing what thing we use to predict, right? And before we actually make our final prediction, I would be interested in actually playing against this model. So what if we jump back over to, what was it, in part 2, we write our little game loop. And so I'm going to grab our game loop. And so in order to actually play a game, we just call play game with whatever function we want to use for the AI. So for us, that's play neural network. I also get ads from random people claiming to 1,000x your income with ChatGPT. Okay, I will say the LLM scams are just flourishing. I feel like we had a season of crypto scams, and now we're just having this glorious season of LLM scams. Okay, so we have a chessboard, and we're playing against an AI that, in theory, should be kind of good, right? We don't know, but let's see. I will make my classic opener of E2 to E4. And they respond by threatening my pawn. Okay, that's fine. I will just, why don't we defend the pawn? Why don't we say our knight in B1 will jump up to C3. Boom. So I defend my pawn, and then they advance their knight. I would say this is, in my opinion, not like the best move ever, but they're not being silly. Why don't we advance our knight from G1 to F3? Okay, things are getting interesting now. I wouldn't have done that, but I guess they're probably trying to get their queen out. So if I take their pawn, then their queen might take. No, they wouldn't do that because I just take their queen. Well, okay, let's take the pawn. Let's get in there. So we'll say E4 to D5 and take their pawn. The first thing that happens is I take their pawn, and then they take the bait, and their queen took our pawn. So now we can just take their queen, and that was pretty dumb of them. So we can say C3 to D5. We took their queen. They then did take our knight, so they weren't so dumb. I guess this is the interesting thing is we're talking about how many turns are you thinking ahead, and I think it has really, really learned that taking pieces is good, right? But it has not fully worked out hey, if I take this piece, but then I end up losing my queen a turn later, that actually wasn't worth it, right? So it is smart after a fashion, is that it'll take the piece when it can see that it can take a piece, but it is not thoroughly versed in sort of the strategy of what's a good trade, right? So given that I'm sizing it up, and it doesn't seem to be that smart. What if I move my bishop from F1 over here to B5? And okay, so they did not take the bait there. But of course now I have to move. Oh, this is okay. So this actually would be kind of a bad. You can't make any invalid moves, which is interesting that when you back this AI into a corner, it starts getting actually kind of decent because it has to make a move that's legal, right? So I think what it just did was silly. I mean, I think another thing that it has learned is that threatening high-value pieces is good. So in this scenario, their knight is threatening my queen, and that's like a pretty good position to be in. But they haven't considered that at the same time they're threatening my queen, I can just take their knight with the pawn. So I could go from d2, say, to c3 and clean up. Okay, but this is cool. I think this is neat because we're really getting to disassemble like what things has it learned, right? And I take its knight, but then it goes ahead and it says, okay, I'm going to threaten your bishop now, right? So it's always doing something that is going to threaten one of my pieces. So it has learned that taking pieces is good and threatening pieces is good. It just has not learned that its own pieces being threatened is pretty bad, which I think is just a very, very interesting way to disassemble like what things has this model learned. But so, of course, the final step here, I think I'm done playing this game, so we can just quit. I think it was interesting, but ultimately it didn't rock my world. But that doesn't mean that our model couldn't actually be okay. Let's see. Let's just delete this whole loop. Well, the loop is fine, I guess. But now let's actually make some predictions. Boom. We can apply. And I guess really we should just submit this and run it. But we can just make sure that things are looking okay. Which another cool virtue of having an ensemble model is that there can be a lot of intelligence in there, but it doesn't always have to take the time to go through all of it, right? So before we had one model, like you're running that whole model for every single move. Whereas in this case, we only have to run 1/3 of our model, basically, right? Only the third of our model that's relevant. Cool, so our predictions look good. And so we can come over here and submit, boom. And we will see how good our ensemble model does. Wait, it should sort of leave the king alone then? If you mean like it wasn't going to allow itself to be put in check, yes. I think the answer to that is yes. Because that just wouldn't be a move that it even considers because that's illegal. Alrighty, well I think we're gonna let this run and see how well it does. Other than that, I think I'm going to do my shill one last time about opportunities to get swag dropped. So we're going to do actually. Okay, I'm going to add one more. Oh, this is an interesting question. No, it goes for the highest value targets, and the king isn't worth any points. No, okay. So I think this is a good question. I think the answer is no, because what it's learned. I mean, it's learned lots of things, and I was kind of projecting like, hey, it knows that it's good to threaten other pieces, right? But notably, our training data is like really, really high quality labels of if a board state is good or not. And like in general, it'd be like if you move to put your opponent in check, or like you move to put them in checkmate, then like that's like the highest value there is, right? Like that would be like worth all the points, right? So I mean, hard to know. We could like assemble a test case and be like, well, what does it do in this situation? And we could kind of probe and find out. And the world of AI explainability is super cool and interesting. But I would say probably it has learned that it wants to threaten the king when it can. But that's a good question. Okay, so the last push here, because I will admit, I like Global Hack Week, but I think there should be more machine learning at it. And so I'm like really trying to pump like, hey, what if we got some Kaglers in Global Hack Week? Like what if we got it going? And so the tool that I have to do this is to throw swag drops at it. That's kind of the tool that I have. I wonder actually. Here's a question: if we found a way to give guild points for Kaggle competitions, would anyone be interested in that? Would that be compelling to anyone? I don't know if that would actually be like actually that interesting or not. But are we still doing guild points? I don't know. But so here are the ways that you can get swag dropped. So right now there are no notebooks in the competition. So if you publish any notebook, and we walk through how to do that. In fact, we can walk through this as well. Here, we can go to share. Once you have a notebook, make it public. Boom. Excuse me. But if you share a notebook right now, any notebook would be the winner. But if you have a notebook that has something cool in it, then that person will get a swag drop. I will say if anybody posts an interesting comment, that can get a swag drop. So we're adding comments to the or discussion if you raise any points. Which honestly, Polar Void, you've been throwing out points left and right that I felt like were very, very interesting and would love to have in a discussion. I promise I'll upvote them. the person who wins at the top of the leaderboard, and then 2 other people who have just made submissions will also get swag dropped. And that is, I think, where we're going to leave things. I think it would, but it may be more popular in just a few guilds. Yeah, no, I think that's fair. I think, like, typically, you know, Blahaj gang goes up and attacks like ES techies, or those are still around, right? ES techies. Yes. Okay. So let's see. Has our submission completed? It's still running. Let's look at the logs. Are we still training? I will say, because it's 3 different. Like you can look at it 2 different ways. One is our models only have to train for 20 epics, but we have to train 3 models, and so okay, like that, does that end up being kind of equivalent to 60 epics? Like, yeah, kind of. But then you're training on 1/3 of the data for each one, so the epics are shorter. You can go back and forth. But it looks like we're probably still in training mode. Let's see, which model are we training now? It doesn't even say what model it is. We could have better logs. I should write better logs. Yeah, they're also smaller, exactly. So there's, I think the world of trying to estimate how long it'll take to train something is like super valuable, and also can be tricky if you're not really writing down all the numbers. But yeah, so these, we have 3 models, and they're all smaller, and they're running on less amounts of data, and they are running for fewer epics, but there are 3 of them. So like, I would guess that overall, compared to our other big model that we played with, that this is just going to run faster anyway. Another thing to think about, okay, great, we generated some predictions, this should be almost done. Yeah, it's doing its conversion thing. I was just about to say that you could run these in parallel. You could get 3 different compute systems, 3 different GPUs. And do we have a score? Does it give us, what's our score? Wait, come on. You got to tell us how we did. Where does it say this on the other note? Oh, there we go. Our score, 0.2. Okay. So decent. I would say the way that I would improve this, and yeah, I think we're out of time, but the way that I improve this is just based on our graphs. This is really getting into the science of it all. But like, this graph looks a little bit closer to like leveling off. But like this graph, there's still plenty of juice in that tank, right? You could just train for another 30 epics and probably still be getting better. So I would probably train all of these for, at least another 10 epics each. Another thing that would be interesting is, so we trained all of these just on the opening or the mid or the end game data, but you could imagine starting each of them on like a random selection of all the data. So like all the models learn a little bit about all phases of chess, and then you go into sort of a second phase where they just get trained on sort of the specific phase that they're a specialist in. This is like another thing to try. I mean, this is kind of what we do with large language models, right? We start by training them on all text, and then we fine tune them on like the specific problem we want them to do. But so our ensemble model, I would say, does better, or at least better than our sort of first take in terms of the score we get. And there's a lot of interesting, like I think there's still a lot of more juice to get out of this kind of setup. You could make the individual models a little bit bigger, you could train them for longer, you could do this sort of fine-tuning setup. But I'd be interested if anybody tries that, if they just cranked up the size of the models in here and trained them for a little bit longer. If you publish that as a notebook, that'd be, I think, to me, very, very interesting and worth a swag drop. They're horrible with conditionals, for example, because of how they execute programs. Oh, the more data you can send through the GPU, which can run in parallel, the better. Yeah, for sure. Yeah, it is interesting seeing like what kinds of tensor operations are like really, really cheap, and then what ones are like, oh, you just want to see like if this one number is greater than another number. Like, no, that's like that's all going to be bottlenecked by CPU or whatever. You could do some adversarial thing here. Wait, what adversarial thing? What are you thinking of? Maybe you shouldn't say on stream. I don't know. Okay, right on. Well, what did we do today? We reviewed some stuff. We checked in on our leaderboard. We looked at overfitting and how to avoid overfitting. We found some bugs in our code. We looked at how to save a model, because as you spend a lot of time training a model, you don't want to have to waste all that computation again and again. And so you find ways to save time by saving your model. We broke chess. Yeah, that's a big one. We learned that the queen is a material girl, as they say. I think that's the quote of this Global Hack Week for me. And then we dove into ensemble models, where you train different models on sort of different parts of your problem and then stitch them all together to hopefully get something intelligent out of it. And that, I think, puts a cap on this Global Hack Week for training an AI to play chess. So thank you so much for participating. The last plug here is that we have about another day for the competition to be over. I will continue to monitor it, and so if you have any questions, or if you want to add your notebook later, then that's totally cool. But yeah, I will monitor the discussion here for any questions you might have if they come up. Other than that, I will say thank you so much for attending this session. All the questions have been great. Alvin, it was great to see you again. And I will say happy hacking, happy Friday, and I will see you at the next Global Hack Week. Bye, friends.